Okay, I guess you can see them. Otherwise, if you have problems in seeing the slides or in hearing my voice, please let me know. Okay, this is the second lesson of the course Analytical Techniques for Wave Phenomena. For those who are here for the first time, basically in the first lesson I introduced the contents of the course and I started speaking about analytic functions, that is, complex functions of one complex variable. This topic is more or less the leitmotif of the entire course. It's an analytical tool which is fundamental in the study of wave propagation in general, so not only electromagnetic waves, which are the subject of my personal interest in particular, but of any kind of wave motion. It could be acoustic waves or seismic waves or water waves, whatever. Basically, in the first lesson, I defined what an analytic function is. It is nothing more than a function which is differentiable. However, since we are dealing with functions of one complex variable, in contrast with functions of real variables, this assumption of differentiability has vast consequences. And the most important of those consequences are the subject of the lesson of today, which will be based on introducing the concept of integral or of integration in the complex plane. So I will start with giving you some fundamentals on complex integration, or also known as contour integration in the complex plane. Well, as in the case of real variables, there are two meanings, two loose meanings of the word integral, also in connection with complex functions. We speak of indefinite integrals, meaning a function whose derivative equals a given analytic function in a given region of the complex plane. So it's the antiderivative, or also known as a primitive function. We are more interested here in definite integrals instead, which are taken over some integration domain in the complex plane, which is a curve, or more precisely, some kind of regular curve, like a piecewise differentiable arc. Now we will see the details. In order to be able to integrate a complex function along this piecewise differentiable arc, of which you can see an example in the bottom part of this slide, it is not necessary that the function you are integrating is analytic. It's enough that it is continuous. So the definition we are going to present of definite integral can be applied, is applicable to any kind of continuous function. Why are we interested in studying definite integrals? The main reason is a theoretical one. That's because without integration, it would be extremely difficult to arrive at some fundamental properties of analytic functions. And so this is the reason we will address this topic at the beginning. The definition of a definite integral is the one you can see in the upper box here. You can see on the left the symbol of integral with gamma at the bottom. Gamma is the name of the curve, that is the integration domain. Then you have your continuous function f of a complex variable z, and then the usual differential. By definition, this is the real integral from a to b of the function f, where the argument now is z, which depends on a parameter t, and then we have the derivative z prime of the function z of t. What is this function z of the real variable t? Well, this is one parametric representation of our curve, so of the arc gamma upon which we are integrating our function f. So the arc gamma is represented in parametric terms as a function z, a complex function z of a real variable t. The parameter t varies from a to b. Okay, those are the integration limits. It's easy to see that if you change your parametric representation, so for the same curve, you adopt a different kind of parametrization, which is something, of course, always allowed, then with this definition, the value of the integral will not change, which is, of course, something desirable. Otherwise, the number you get would depend on the way you parameterize your curve. That's easy to see because if you change parameter from t to tau, for example, through a function phi, where now the integration limits on the new variable tau are named alpha and beta, where a corresponds, of course, to alpha and b corresponds to beta through the reparameterization phi, then you see immediately that z is a function of the new parameter tau by the properties of the composite functions. If you calculate its derivative, which occurs in the definition of the integral given in the box above, then you will see that z prime of t can be written as a product of z prime of phi of tau times the derivative phi prime of tau. And so this gives you directly the right-hand side, which is the integral with respect to the new parameter tau, which has exactly the same form as the integral with respect to the parameter t in the box above. So what we get is that in the end, we obtain exactly the same numerical result with any parametric representation of the same curve. Okay. With this definition, we have a number of properties of the integral. We shall list some of them. For example, we can define integration along the opposite arc. So instead of integrating on gamma, we now integrate over minus gamma. And by definition, this is the integral from b to a instead of from a to b. Whatever else remains the same. So, of course, this has the same value as the integral upon gamma, but with a different sign. Okay. In a drawing, we would indicate the direction of integration along our arc with an arrow. So on the left picture, in the left picture, you can see we integrate from A to B, whereas on the right picture, we go the opposite direction from B to A. Okay. Some further elementary property is the additivity. That is, if we have a collection of curves, or better, or arcs, gamma 1, gamma 2, and gamma n, then we can define the integral upon the whole collection as simply the sum of the integrals over each of those arcs. In case those arcs are subsections of a given arc, as in the picture on the left, then this is a property of the integral, that is the additivity of the integral with respect to splitting the integration domain into parts. Whereas if the arcs are disjoint, as on the right part of this slide, then this is a definition. So basically, the right-hand side of the equation above defines the meaning of the integral which is written on the left-hand side. Okay, so this is very natural, of course, but it must be stated explicitly. Let us see the relation of this integration, this definite integral, with another kind of integral, which is similar, that is the integral with respect to the arc length. If we take the absolute value of the definite integral of the function f over the arc gamma, then by elementary properties of the integrals, we can see that this absolute value is less than or equal to the integral of the absolute value of the function f. Of course, f is a complex function, so in this case, we are speaking of absolute value of complex numbers, times the absolute value of the differential, which in turn is the absolute value of z prime times the differential of the parameter t. Now, the latter quantity is, of course, the elementary arc, so the elementary length of the arc, what we usually write as ds. So what we get in the end is the integral with respect to the arc length of the absolute value of the function f. This is something, of course, real, because the absolute value of anything is a real quantity. And it's not only real, but it's positive. So this integral is a real integral of a real function, and it gets a real number, a positive real number as a result. So we have the possibility to compare the absolute value of a complex definite integral with the integral with respect to the arc length. And just to give you an elementary example, if we take the exponential function, the exponential of jz as the integrand, and we parameterized our curve gamma, as you can see here in orange. So z is equal to r, a fixed number, times e to j phi, where phi is an angle that goes from phi 1 to phi 2. And phi 1 and phi 2 are belong to the interval between 0 and pi over 2. What you get is, of course, a parametric representation of an arc of a circle, as you can see in the picture. And so we go from phi 1 to phi 2 on this arc, so in anti-clockwise direction. If you calculate your integrand function on this arc, then what you get is a complex value, of course, whose absolute value is equal to the exponential of minus r sine phi, and whose argument is instead r times cosine phi. So now we are in a position to make the calculations. In particular, the absolute value of our definite integral along this arc of the exponential function exp of jz, this is less than or equal to the integral with respect to the arc length of the absolute value of the integrand, which again is the exponential of minus r sine phi. And this quantity is less than its value in calculated at the smallest angle, phi 1. So we can write that this is less than or equal to this smallest value, this largest value, sorry, not smallest, but largest value, which can be taken outside the integral. And what remains inside the integral is just the constant equal to 1. So in the end, what we get is the length of the arc gamma, which is equal to the radius r times the difference phi 2 minus phi 1. So we have obtained the result that the absolute value of the integral of the exponential e to jz on the considered arc gamma is less than this quantity here. And the significance of this result, for example, in a practical calculation, can be that if you now let the radius r go to infinity, then this quantity goes to 0, because there is this exponential here that wins against the factor r, and so everything goes to 0. So this is something that may be useful in practical calculations, as we will see at the end of this lesson. Another way of defining the same kind of integral is in terms of real differential forms, and this can be done by separating the real and imaginary parts of everything. So if you write your integrand as u plus jv, where u and v are the real and imaginary parts of your function, and you do the same inside the differential, so you write the differential as dx plus j dy, and then you split the real and imaginary parts of the integral, what you get is what you can see here, where you will find real integrals in the plane of real differential forms, which are nothing than the usual integrals, line integrals of vector fields in 2 dimensions, of course, whose definitions are the usual ones in terms of the parametric representation of our integration domain. It's useful to recognize this connection with the real differential forms, because we know many things about the integrals of real differential forms. For example, we are able to characterize the situation in which this line integral of a differential form does not depend on the path of integration, but depends only on the endpoints of the integration path. In particular, the theorem is the one stated in the box. The line integral of a real differential form, p dx plus q dy, along a given arc gamma, which is contained in some open set omega of the 2-dimensional plane. Well, this integral depends only on the endpoint of the arc if and only if there exists a function capital U defined in omega, whose partial derivatives are equal to p and q when they are made with respect to x and y. And this is, of course, something very well known. This tells us that a two-dimensional vector field V, whose components along the axis are p and q, this is conservative if and only if there exists a scalar potential U, capital U, of this field. That is, we are able to write the vector field V, as here in the bottom line, as the gradient of this scalar potential U. Okay, this is extremely important because now, coming back to our complex integrals, if we apply this property to our definite integral of the complex function f along an arc gamma, then by writing this integral, as you can see here on the top, that is by splitting the differential into dx plus j dy, then if we apply the theorem we have just stated, we will see that this complex integral, definite integral, will depend only on the endpoints if and only if there is sort of complex potential, scalar potential, we will call it capital F, whose properties are that its partial derivatives with respect to x or with respect to jy are equal to the given function f. Now, this is a way of writing compactly the condition that the partial derivative of capital F with respect to x is equal to minus j, the partial derivative of capital F with respect to y, and in turn, this is a compact way of writing the so-called Cauchy-Riemann equations. This is something we saw in the first lesson. They are a pair of relations, of differential relations that characterize the differentiable or analytic functions. So basically, we have that, to summarize, the integral of a complex function depends only on the endpoint if and only if this function can be obtained as the derivative of an analytic function, capital F. And in this condition, we will see in half an hour or so that the function f itself, so small f, is analytic itself. What if our integration domain is a closed curve? Well, you all know that the independence of the integral on the arc, but its dependence only on the endpoints, is equivalent to saying that the integral along any closed curve is equal to 0. So, if our function is the derivative of an analytic function capital F inside our open set omega of the plane, then we have the additional result that its integral along any closed curve, that integral must be equal to 0. And as I said, under these conditions, f of z itself is an analytic function. But we will need some more results to prove the latter statement. Okay, let's give some example. Sorry?
Can I ask a question?
Sure.
But this means that basically an anamorphic function is derivative infinitive time. So it's
exactly.
Okay.
An anamorphic function can be
in the complex domain. If it's derivative, it belongs to C infinitive, basically.
Yes, it's even more than C infinity, because the class C infinity technically is that of functions which can be differentiated as many times as you wish. Okay, but analytic functions not only are functions that can be differentiated any times you wish, but they are the sums of their Taylor series. So if with those infinite derivatives you build a Taylor series, then it turns out that this Taylor series converges to your function, if that is analytic. So the class of analytic functions is even more special than the class of C infinity functions, because it can be easily shown that there are functions which are in C infinity, but which are not analytic. So they are not the sum of their Taylor series. Okay. So indeed, analytic functions are very special, and we will see this in a moment.
Okay, thank you.
You're welcome. Okay, just to give you some examples of integration along closed curves. For example, if you consider monomials like z minus a to n, then the integral along any closed curve of this kind of function must be equal to 0, provided that the exponent n is different from -1. And this is simply a consequence of the fact that z minus a to the nth power is the derivative of 1 over n plus 1 times z minus e to n plus 1. So it's the derivative of a monomial, which we know is an analytic function. And so since it is the derivative of an analytic function, its integral along any closed path, as we have just said, it must be equal to 0. The only exception occurs when the exponent is -1, as we can see immediately if we take a circle which goes around our point A, and we parameterize this circle in the most natural way as a plus rho, the radius, times the exponential e to jt, where t is the parameter that goes, of course, from 0 to 2 pi in order to cover the circle entirely once. So if we calculate the value of the integral of the function z minus a to -1, which is written here as a fraction, so 1 over z minus a, then it's immediate to see that this is equal to the integral from 0 to 2 pi of j in the t. And this is not equal to 0, but of course it's equal to 2 pi times j. So in this case, this is an example of a function which cannot be derived from cannot be represented as the derivative of an analytic function. Since we know, however, that 1 over z minus a is locally the derivative of the logarithm function, what we have shown here is basically that the logarithm function cannot be analytic in the entire plane. Because if it were analytic in the entire plane, or even less in the entire annulus from the radius ρ1 to the radius ρ2, well, if this were true, then this integral we have just calculated would be 0, and instead it is not 0. So in some way, the logarithm cannot be defined as an analytic function in the entire annulus. And as we saw in the first lesson, this is a consequence of the fact that in order to define the logarithm, we have to cut the plane along certain paths, the so-called branch cuts. And once you cut the plane, then you will end up cutting also the annulus that is represented here. So inside the annulus, you have a discontinuity along the cut. Okay. Okay, now we come to a very important definition, which is fundamental for the following, that is the index of a point with respect to a closed path. This is a sort of generalization of the example we have just seen. The theorem can be stated as follows. So let gamma be a closed path, any closed path, not necessarily a circle. Let omega be the complement of gamma. So in simple terms, there will be an inside and an outside. And let us define the function index of the point z with respect to this closed path gamma as the right-hand side says, so 1 over 2 pi j times the integral over gamma of the function zeta minus z, where zeta is now a complex variable, of course. And so this is an integral in the complex zeta plane. Now, this index function turns out to be an integer valued function on omega. So it can only assume integer values. And those values are constant in each component of omega. So if you consider, for example, gamma as a circle, then omega is constituted by two components, the inside of the circle and the outside of the circle. The outside of the circle is, of course, unbounded. So there is an unbounded component in omega. And this index function turns out to be 0 in the unbounded component of omega. Okay. What's the meaning of this index? Well, this is an example. If A1 is the point we are considering, and the curve is the gray one shown in this slide, then we have that the index of A1 with respect to this curve, gamma, is equal to 1. Whereas if you consider a different point, A2, which is in the unbounded component of the complement, so it's outside basically the curve, then the index is equal to 0. Now, since it can be shown quite easily that 2 pi times the index is equal to the net increase of the argument of the quantity z minus a, where z runs along our closed path. Okay, then if we divide this increase by 2 pi, we obtain simply the number of times that gamma wins around your chosen point A. So the index tells you how many times your curve wins around the chosen point. And for this reason, it's also known as the winding number of gamma with respect to A. So as you can see in this example, A2 being outside the curve is such that the curve does not wind around A2, whereas the curve in this example wins exactly once around A1, so the index is equal to 1. The index appears in many fundamental ways in the theory of complex analytic functions. In particular, we will see its appearance in what is probably the most important theorem of the entire theory, which is the so-called Cauchy Theorem. We will start with a local version of the theorem, and we will end this lesson with a global version. This theorem was stated by Cauchy in the first years of the 19th century, assuming that the function we are integrating is differentiable and its derivative is continuous. Edmond Goursat, another French mathematician, discovered at the end of the 19th century that it is not necessary to assume that the derivative is continuous. So it's only necessary to assume that the function f we are integrating has a derivative, so is analytic. As you can see in the statement of the theorem in the box, if we have omega, which is a convex open set, note that now we are explicitly assuming the convexity of the open set. If P is a single point inside this open set, if f is a continuous function defined in omega, which is holomorphic, that is analytic, inside omega with the exception of this single point P, then it turns out that your function f is the derivative of some holomorphic function capital F defined in omega, and for what we have said as a consequence, the integral of your function f along any closed path is equal to 0. So basically what you need to know is that your function f is holomorphic in omega, and there can be also an exceptional point. Actually, this exceptional point we will see is not really exceptional, so we will discover that the function can be defined also at this exceptional point as holomorphic, but it's useful to formulate the theorem in this way, because in this way it's easy to get what is known as the Cauchy integral formula.
Hello,
Yes?
I want to ask some question.
Sure, please.
Sir, kindly tell me what is H and what is
Okay.
holomorphic.
Okay, yes, this is something we saw in the first lesson. H is the class of holomorphic functions. The word holomorphic has the same meaning as analytic, and this means a function which can be differentiated, a complex function of one complex variable which admits a derivative. Okay, so if you see holomorphic, this means that the function can be differentiated. And the class of holomorphic function is indicated with letter H, and the argument is the domain of holomorphy or analyticity of your function. So the domain of points in the plane where the function is holomorphic. By definition, this set must be an open set. Okay?
Okay, it doesn't mean H points H is outside or inside the contour.
The point P, or maybe I didn't catch your question. Can you repeat, please?
H
H.
function. H function contain all points inside the contour and outside the contour.
H is not a function. H is a set. H
Okay.
is a set of analytic functions defined in, for example, omega or omega without the point P.
Okay.
Okay.
Okay. Got
The
it.
integration domain gamma belongs to omega.
Okay. Got it.
Okay.
Thank you. Thank you.
Okay. So this theorem, the Cauchy theorem, is the basis of the so-called Koshik formula, which we will present here for a convex set. If we now have that gamma is a closed path in a convex open set omega, and we know that our function is analytic inside omega, then if you pick a point, an arbitrary point z inside our domain omega, and if you assume that this point does not belong to the closed path gamma, then you can write this fundamental relation which tells you that the value of the function f at the chosen point z multiplied times the index of z with respect to gamma is equal to the right-hand side, which is 1 over 2 pi j of the integral of the function f, now calculated with the argument xi, divided by xi minus z. Note that if the curve does not wind around the point z, so the index is equal to 0, then this tells us that the right-hand side is equal to 0. Otherwise, we have a representation of the function f inside the curve gamma. So basically, this is a representation formula, a fundamental representation formula, which tells you that if you know the value of an analytic function on the boundary of a finite domain, then basically this is enough for knowing the function everywhere inside this domain. Because as you can see, the left-hand side contains the value of the function f calculated at an arbitrary point z inside the closed path gamma, whereas in order to be able to calculate the right-hand side, what you need is just to know the function f on the boundary of the domain, so on the integration path gamma, okay? Which is something not trivial and which has many profound consequences that we will start now to enumerate. The first fundamental consequence of the Cauchy integral formula is the representability of any analytic function as the sum of its Taylor series, which is something we were discussing before. For every open set omega, if you have a function that is analytic in this open set, then this is representable by power series in omega, which means that if you take any point A inside this domain omega, as you can see in the picture, and you consider any disk entirely contained inside the domain omega, the disk is in green in the picture with radius r, then if you apply Cauchy integral formula to the boundary of this disk, you are able to represent the function f as the integral here over the boundary gamma of this disk. And now, inside this disk, you have the property that 1 over xi minus z is the sum of a geometric series. And this geometric series, we saw it in the previous lesson, converges because on the boundary and inside the circle, basically the absolute value of the ratio between z minus a and xi minus a is less than 1. Under these conditions, not only the geometric series converges on the boundary, but it does so uniformly. So we are, it's possible to exchange the infinite summation and the integral. Okay, this is something which is done at the bottom of the slide. If you do this exchange, you end up with a power series in powers of z minus a, whose coefficients are here called Cn, are expressed in turn by integrals. But the important point is that it is guaranteed that this power series converges, and it converges to the given analytic function f. So we have discovered that any analytic function is representable by a power series, and from what we said in the previous lesson, this means in turn that the function f can be differentiated anytime you wish. And so, as a consequence, the derivative of any analytic function, being itself representable in terms of power series, must be an analytic function itself. So every complex differentiable analytic function is infinitely differentiable, as we were saying before. So it's C infinity. It's in C infinity because its derivative is itself analytic. Well, this is in striking contrast with what happens with real functions of one real variable, for which you can easily imagine examples of functions which can be differentiated only once in a point, at a point. Whereas if you consider a holomorphic function, once the function is holomorphic, that is differentiable, then automatically it can be differentiated anytime you wish inside the domain of analyticity, of course. But there is even more. For example, we can deduce another consequence from all these properties, which is the so-called Morera Theorem, which is in a sense a converse of the Cauchy Theorem, because the Cauchy Theorem assumes that your function is analytic and tells you that its integral along any closed path is 0. Morera Theorem does the opposite. So if you have now a function f, which is assumed to be only continuous, and for which you know that the integral along any closed curve gamma is equal to 0 when we are inside an open set omega, then as a consequence, now we have that the function must be holomorphic inside omega, that is analytic. And the proof is extremely simple. As we know, if a function has the property that its integral along any closed curve is 0, then it must be the derivative of some holomorphic function, capital F, its scalar potential. But now we know that the derivative of any analytic function is itself analytic, so we have immediately the conclusion that F must be itself analytic. And this concludes the proof, of course. Okay. This is useful in many proofs, okay, to be able to invert Cauchy theorem. Okay, before going on, if you agree, I would make a break. Usually I will break the lesson in 2 parts. So now I will stop for, let's say, 10 minutes, and then we will go on drawing some more consequences from the Cauchy theorem. In particular, we will talk about the zeros of the analytic functions. Okay, so see you in 10 minutes or so.
Okay, see you later. Thank you.
Thank you.
Thank you.
Okay, I'm back here. I think we can start over. Can you hear me?
Sì.
Okay, great.
Yes.
Thanks.
Yes.
Okay, we will go on drawing some further consequences from the local Cauchy theorem. In particular, we will say now something about the zeros of an analytic function, that is, the points of the complex plane where an analytic function is equal to 0. The theorem, in particular, says that if omega is a non-empty connected open set, and f is a function which is analytic in omega, we then may define the zero set of this function as the collection of points A belonging to omega, where the function f is equal to 0. Then we have a characterization of this zero set. Either the zero set is the whole non-empty set omega, so the function is identically 0 in omega, or otherwise the zero set has no limit point in omega. So it's made of single discrete isolated points, and in the latter case, there corresponds to each A in the zero set, so as we will say, to each 0 of our analytic function, a unique positive integer m, which depends on the 0, of course, such that the analytic function f of z can be represented as the product of the monomial z minus a at the mth power times g of z, where g is holomorphic in the entire domain omega. G is different from 0 at the point a, and m is an integer, as I said. Furthermore, the zero set is at most countable, so there can be an infinite number of zeros. However, this is a countable infinity, which means that you can establish a one-to-one correspondence between the set of the zeros and the integer numbers, so you can count them. The integer m is called the order of the 0, which your function f has at the point a. Now, this is an important theorem. For example, as a consequence, if you know that two functions are analytic in the same set omega, let's call them f and g, and if you know that f and g are equal for all the points z in some set, which has a limit point in omega, then as a consequence, the two functions f and g must be equal to all z in omega. So this is a uniqueness theorem. It's enough to know an analytic function in a subset of omega, which has a limit point in omega, to have basically the uniqueness of the function. There is only one analytic function that has those values if the set has a limit point in omega. So this is a very powerful property, which is not, of course, shared in any way by real functions of real variables, even differentiable functions of real variables. Now we will talk instead about singularities, and we will start with the simplest kind of singularity, the isolated singularity. If we have a point A inside the domain omega, and if we know that our function f is analytic inside omega with the exception of this point A, then we say that our function f has an isolated singularity at A. So a single isolated point where it fails to be analytic. So what happens in the neighborhood of such an isolated singularities? Well, the nicest thing that can happen is that the function f can be defined also at this singularity in such a way that this extended function is analytic in the entire domain omega. Well, in this very lucky situation, the singularity is said to be removable, basically because by an extension of the definition of the function, you can remove it and get an analytic function in the totality of the set omega. It turns out that this occurs if and only if our function f is bounded inside the neighborhood of the isolated singularity, so inside the so-called punctured disk, so the disk the circular disk having center at the singularity A and having radius r, however, without the center. So the point A is excluded from this disk, and for this reason the disk is indicated with a prime, okay, d prime. If we know that our function f is bounded inside this disk with a hole, okay, for some radius r, then we can conclude that the singularity is removable. And this is quite simple to see. For example, we could define a new auxiliary function h to be equal to 0 at the isolated singularity A, and at any other point it can be defined as the product of our function f of z times the monomial z minus a to the second power. Now, the assumption of boundedness of f has the immediate consequence that our function h can be defined everywhere, and is differentiable everywhere, and its derivative at the point A is equal to 0. So as a consequence, we have a power series representation of the analytic function h, a Taylor series, which, however, will start from the order n equal 2, because the function has a double zero at the origin, okay? And now, if we define the function f by letting f at the singularity A equal to the first of the Taylor series coefficients, so C2, then it's easy to see that if you define the function f as this power series at the bottom, where now n goes from 0 to plus infinity, and the coefficients have a shifted index, n plus 2, as you can see in the subscript, then it's easy to see that this function here is equal to the original one everywhere in the disk without the singularity, and it's equal to C2 at the singularity being defined as a Taylor series, so therefore being an analytic function everywhere. So we have effectively removed the singularity. As I said, this is a lucky situation. If your function is not bounded in a neighborhood of the singularity, then this cannot be done. And what happens instead? Well, here we have a classification of what happens in any kind of singularities, isolated singularity. We have three possibilities. The first one is that f has a removable singularity. Otherwise, it is possible that there are numbers, C1, C2, up to Cm, where m is a positive integer. All those numbers are different from 0. Sorry, the highest order number, Cm, is different from 0, such that the difference between our function f and the sum of the rational functions ck over z minus a to k, well, this difference has a removable singularity at a. So even though our function f has not a removable singularity, however, by subtracting suitably chosen rational functions like those ones from the function itself, then we manage to obtain a removable singularity. In this case, we say that our function f has a pole singularity of order m at the point A. And the rational function we have subtracted from f in order to get a removable singularity is called the principal part of f at A. And it's easy to see that because of this principal part, the function f is not bounded in a neighborhood of a pole, and its absolute value tends to infinity if you approach the point A, so the pole. But there is a third possibility, let's say the most complicated one. It is possible that the function does not have a removable singularity, and it does not have a pole. The remaining possibility is called an essential singularity, and this is point C in the box. In this case, if you have an essential singularity, it turns out that if you consider any positive radius r, and the disk having center at the singularity and radius r belonging to the domain omega, then the image of this disk without the singularity, of course, is a set that is dense in the complex plane. this means that in any neighborhood of an essential singularity, the function f sends the neighborhood to points scattered everywhere in the complex plane. So it's a completely crazy behavior of the function in a neighborhood of the essential singularity. What does it mean, dense? It means that the image points of the neighborhood of the essential singularities come as close as you wish to any point in the complex plane. So you can approximate as well as you wish any point in the complex plane by moving in a neighborhood of an essential singularity. So this is a very complicated behavior. Let us extend all these considerations about zeros and singularities to the point at infinity in the complex plane, because it's very useful for many purposes to add the point at infinity. In order to do that, we can resort to some geometric representation of the complex plane, the so-called stereographic projection. So imagine your complex plane is this horizontal plane in cyan here, which bisects a sphere, okay, of an arbitrary radius, for example, of unit radius. We have a north pole, a south pole, and we establish a correspondence, a one-to-one correspondence between the points in the plane, the complex plane, so for example, this point Z, and points on the sphere by simply tracing the line between the complex point Z and the north pole of the sphere, and finding the intersection of this line with the sphere. Let us call this intersection capital Z. Well, this is the point on the sphere that corresponds to our complex value Z. It is clear that in this way we get a one-to-one correspondence of all points of the complex plane to all points of the sphere, with the exception of the North Pole, which will never be reached in this way by this geometrical construction. Well, the point at infinity of the complex plane can be thought of the single point that can be added to the complex plane in order to get a one-to-one correspondence with the entire sphere. So it would be the point of the complex plane that corresponds to the North Pole. Now, this is to visualize, of course, the point at infinity, which in a sense completes the plane. Let me add, okay, we have an additional guest. Welcome. If you add the point at infinity of the complex plane to the complex plane, basically you complete it in the same way that if you add the North Pole to the sphere, that without the North Pole, you complete the sphere. So basically it's a way to make the complex plane a compact object in topological terms. It's useful because now, if we have the point at infinity, we can speak of the behavior of a function at infinity. We can speak of a neighborhood of the point at infinity, which is, of course, the set of points whose absolute value is larger than some given number, capital R, for example. The value of a function at infinity may not be defined, but we will treat the point at infinity as an isolated singularity. So by convention, we will say that the character of such a singularity will be the same of the singularity at the origin of the function g, which is obtained by replacing z with 1 over z. Okay, so if you calculate your function f in 1 over z, as you can see here at the bottom, what you get is a new function g. And of course, the point at infinity, z, corresponds now to the origin. So we can study the origin, the behavior of the new function g at the origin, and decide if this isolated singularity is removable, or if it is a pole singularity, or if it is an essential singularity. And then we will say that the same behavior is the behavior of the function f at infinity. So if the function g, for example, has a pole at the origin, then the function f is said to have a pole at infinity. For example, any polynomial has a pole at infinity. Whereas, for example, the exponential function has an essential singularity at infinity. Okay. Now, let us say something more about the representability in power series. We have seen that any analytic function is the sum of its power series. If we calculate this power series on a circle with center at the point A, what we get is, of course, a trigonometric series, because we get basically a sum of complex exponentials of the kind e to j and theta, okay, where theta is the polar angle in the plane. And as any trigonometric series, it is possible to calculate its coefficients by means of the usual integral representation of the Fourier coefficients, which tells you that the Fourier coefficients can be obtained by integrating from minus pi to plus pi your periodic function f, multiplied times e to minus j and theta, of course, and then dividing the result by 2 pi. And we can exploit all the properties of Fourier series. For example, we can also enforce the so-called Parseval formula, which tells us that if you sum the square of the absolute values of the Fourier coefficients from 0 to infinity, the index n goes from 0 to infinity, then what we get is equal to the integral of the absolute value of the square of your function from minus pi to plus pi divided by 2 pi. Okay. And as a consequence of this, we have that since we know that the coefficients of the power series are related to the derivatives of the function at the point A divided by the factorial of n, of course, because any power series is the Taylor series of its sum, then if the function f is holomorphic in a disk of radius capital R, and if the function is bounded, that is, its absolute value is not larger than the number m for all points, say, in this disk, then it's easy to get an estimate, the so-called Cauchy estimate, about the absolute value of any derivative of the function at the point A. In particular, it turns out that the absolute value of the derivative, the nth derivative of the function at the point A, is never larger than the quantity n factorial times m divided by the radius of the disk to the nth power, which is something useful because it can be used to derive further consequences about the behavior of the function. One of those consequences is a classical theorem, the Liouville theorem, which tells us that every bounded entire function is a constant. We recall that an entire function is a function which is analytic in the entire complex plane, like, for example, the exponential function. However, the exponential function is not bounded, as we know well. It's enough to calculate it on the real positive axis, and we discover that the exponential function is unbounded. But if you have an entire function which is bounded everywhere in the complex plane, then it must be a constant, so a very trivial kind of function. And it's immediate to see then that, because if you know that your function is bounded, that is, its absolute value is less than m for any complex number z, then for what we have said from Parseval theorem, we have that the sum of the squares, the absolute value squared of the Fourier series coefficients, which is equal to the integral we have said before, well, this sum must be less than m squared. This is because we can use the boundedness of f in order to estimate the integral on the right-hand side. And this is possible for any radius r only if all those coefficients Cn are equal 0 for all n larger than or equal to 1. And this fact that every bounded entire function is constant has in turn as a consequence, for example, the so-called fundamental theorem of algebra, which tells us that any polynomial with complex coefficients has at least one complex root. So any polynomial has a root in the complex plane, and if it has one root, it has actually all its roots in the complex plane. So as an exercise, you could try to use Liouville theorem to derive this fundamental fact about polynomials. Another consequence of the Cauchy estimates is that if you apply the the representation of C0, so the first term of the power series, in terms of the representation of the Fourier coefficients, what you get is this integral representation of the coefficient C0. Now, the coefficient C0 is nothing different from the value of the function at the point A. So this integral representation tells us that the value of the function at the point A is equal to the average of the function calculated on the circle of radius r, because this integral divided by 2 pi is nothing but the average of the function defined on the boundary of the circle. And so we have the classical maximum modulus theorem, which tells us that if omega is a non-empty connected open set, f is a function analytic in omega, and the closed disk D with center A in radius r is contained in omega, then the absolute value of the function f at the point A is less than or equal to the maximum that the absolute value of the function attains at the points of on the boundary on the disk. And the equality holds only if f is identically constant in its domain of definition. So, as a consequence, we have that the absolute value of the function f cannot have any local maximum at any point inside omega, because if it had a local maximum, this value could not be less than or equal to the maximum over the boundary of the disk. So basically, we have that analytic functions have no interior maxima nor minima of their absolute values. So the absolute value gets its minimum and maximum values on the boundary of the domain of analyticity. And this is true also separately for the real and imaginary part of an analytic function, since we saw in the previous lesson that the real part and the imaginary part of an analytic function are harmonic functions, that is, functions which satisfy Laplace equation in the plane or in the domain of analyticity. Then, as a consequence, we have a maximum modulus theorem also for harmonic functions. Also, it is true that any harmonic function cannot have any inner minimum or maximum. Its maxima or minima are attained on the boundary of their domain of definition. Okay. Okay, and now in the last part of this lesson, we will address a global version of Cauchy theorem. I remind you that the version of the Cauchy theorem we have been discussing so far was applicable not to any arbitrary open set in the plane, but only to convex open sets. We will now remove this restriction, and in order to do that, let now a cycle gamma, capital Gamma, be defined as the union of some closed curves, gamma 1 up to gamma n. Okay, so we say that the cycle is a union of some closed curves. The global version of the Cauchy theorem says the following. If you have a function that is analytic in omega, where now omega is an arbitrary open set, not necessarily convex in the complex plane, and gamma is a cycle in omega that satisfies the property that it does not wind around any point outside omega, so the index of all points alpha that are not in omega is equal to 0. Okay, for such a cycle, it results that the Cauchy integral formula holds. So let me enlarge the function f of z times the index of the point z with respect to gamma, which should be now capital Gamma. This is a typo. This is equal to 1 over 2 pi j times the integral over gamma of f of xi divided by xi minus z, so the usual Cauchy integral formula. And furthermore, the integral around the cycle of the function f is equal to 0. As a consequence, but this is stated explicitly here in this box, if you have two cycles, gamma 0 and gamma 1, both in omega, which have the property that the index of any point alpha outside omega is the same for the two cycles, so the index with respect to gamma 0 is equal to the index with respect to gamma 1, So basically, those two cycles wind the same number of times around any point which is outside omega, then we may conclude that the integral of your function f over gamma 0 is equal to the integral of the function f over gamma 1. So we have a criterion for deciding when the integration domain can be changed without changing the value of the integral itself. For example, take omega as the domain in cyan here, which, as you can see, has a hole in it, because there is a white part here which does not belong to omega, and consider the cycle capital gamma constituted by the union of those two closed curves, gamma 1 and gamma 2. Gamma 1 winds in anti-clockwise direction around the hole, whereas gamma 2 does it in the clockwise direction, okay? If you have a function analytic in omega, so f is holomorphic in omega, then we may conclude that the integral around gamma of this function is equal to 0. That's because gamma does not wind around any point outside omega. It does not wind trivially around any point in the unbounded component of the complement of omega, but it does not wind also around any point inside the hole, because gamma 1 winds once in anti-clockwise sense, but gamma 2 winds in the opposite direction, so the net sum of the winding number is equal to 0. In this example, therefore, the global Cauchy theorem cannot be applied to the single path gamma 1 or to the single path gamma 2, because, for example, gamma 1 winds around the points inside the hole. So we are not in the position of applying Cauchy theorem to gamma 1, but we can apply Cauchy theorem to capital gamma, that is the union of gamma 1 and gamma 2, because it does not wind around any point, as I said, in the complement of omega. As a consequence, if we now change the direction of gamma 2 in order to let it also wind in an anti-clockwise direction, then we may conclude, as the theorem said, that the value of the integral made around gamma 1 is equal to the value of the integral made around gamma 2. So we have, as I say, the criterion to change the integration domain, the curve, without changing the value of the integral. Note that it can be proved that if gamma 1 and gamma 2 can be continuously deformed one to another, and there is a mathematical precise way of defining what this means, a continuous deformation of a curve into another, still remaining, of course, within omega, then it can be proved that the winding number does not change for any point outside omega. So we are in the position of saying that the value of the integral does not change. Okay, and this is useful in applications. In particular, the most important application of this property is the so-called residue theorem, for which we need a further definition. We say that a function f is meromorphic in an open set omega of the plane if there exists a subset A of omega with the following properties. This subset A must have no limit point in omega. The function f must be analytic in omega without A, so A is a set of points where the function is not analytic. And finally, f must have a pole at each point of A with a given principal part, which you can see written here in terms of the coefficients ck. So basically, a meromorphic function is a function which is not analytic in omega because of the presence of isolated singularities, which are poles. And those poles do not have a limit point in omega. If we are in this condition, then we call the number C1, the coefficient of z minus a to minus 1 in this principal part, we call it the residue of f, of the function f at the point A, and we write C1 is equal to res of f at A. Okay, with this definition, we can state now the residue theorem. Suppose your function f is a meromorphic function in omega, and let A be the set of its poles. If capital gamma is a cycle inside omega without A, so inside the domain of analyticity of the metamorphic function, and gamma is such that it does not wind around any point outside omega, so the index of any point alpha not in omega is equal to 0, then we can say that the value of the integral of the function f over the cycle gamma divided by 2 pi j, the left-hand side here at the bottom, then this is equal to a discrete sum over the poles. Each term of the sum is the residue of the pole at the pole A times the index of the pole with respect to the cycle gamma. This summation may be a finite summation if we have a finite number of poles. In many applications, there will be just one or a few poles. It can also be an infinite summation if we have an infinite number of poles, and in this case, it will be a countable infinity. So you can arrange the summation with respect to an integer index. Okay, this also may happen in some case. So what is the importance of the residue theorem? Basically, it allows you to calculate integrals around cycles, so closed paths in the complex plane, by knowing the value of those numbers, the residues at the poles of your function. And this in turn may be used in a number of situations. For example, in a number of cases when you have to calculate a definite integral, also a real integral, and sometimes it is impossible to obtain the result unless you extend the integral in the complex plane and you make use of the residue theorem.
I ask, sorry, because
sure.
In the previous slide, what does it mean that A has no limit point in gamma?
In omega. Well, it's in the usual sense that A can be constituted by an infinite number of points. Okay, if it has only a finite number of points, then the condition A is not applicable.
Countable and
if A has an infinite number of points, then it is possible that those points, which will be countable, will accumulate in the neighborhood of some point. Okay. If this happens, however, the limit point must be outside omega. So it could be the boundary of omega, for example, which is not in omega because omega is an open set. Okay. So imagine, for example, to give you an example, that omega is the open disk with center at the origin and radius 1. Okay. Mm-hmm. And imagine that we have a set of points that go from the origin to 1/2 and then 3/2. And then 4/3, and then 5/4. Okay, set of discrete points on the real positive axis, an infinite number of those discrete points whose accumulation point is the point 1 on the real axis. Okay, so this is a situation in which the set A has a limit point, which is the point 1. This point is on the boundary of the circle, and it does not belong, therefore, to the open circle. Okay. So in this situation, the theorem can still be applied. What you have to avoid is that your limit point belongs to omega, because in this situation, the residue theorem does not hold. I hope this was clear.
Yeah. More or less is clear. So in this way, the metamorphic function is nothing but a definition of an integrable function for the complex.
Yes, it's an analytic function which has poles and not essential singularities. And those poles do not accumulate at interior points of the domain of analyticity. If they accumulate on the boundary of the domain of analyticity. Okay. The most common situation is that you have a finite number of poles, so you don't have to care about any accumulation. But it is possible that you also have an infinite number of poles. However, in this case, you must be sure that they do not accumulate around any any point inside omega. Okay.
Okay. So basically, if a function is holomorphic and has a finite number of poles,
it's of course meromorphic.
It's meromorphic.
Sure. Yes. For example, a rational function is meromorphic at the ratio of two polynomials, because we know that a rational function has poles at the zeros of the denominator. Since the denominator is a polynomial will have a finite degree and therefore a finite number of zeros, and therefore your rational function will have a finite number of poles. Okay.
Okay.
And that's a meromorphic function.
Okay, thank you.
Okay. Okay, let us give an example of using the Cauchy the residue theorem for the calculation of some integral. For example, we could wish to calculate this improper integral, the integral from minus a to plus a of sine x over x times the exponential e to jxt with respect to t, and then let a go to infinity. So this is an improper integral, which would be the improper integral along the entire real axis of the sinc function times the exponential. So it's the Fourier transform, actually, of the sinc function, which we know, of course, very well is the rect function. But now we will provide a rigorous proof that the Fourier transform of the sinc function is the rectangular function. In order to do that, since the integrand is an entire function, even though we see there is a denominator, when you replace x, the real variable x, with the complex variable z, you could imagine that the denominator z could produce a pole at the origin, because z is equal to 0 and at the origin, but also the numerator sine z is equal to 0, and as you all know, the ratio sine z over z has a removable singularity because it has a finite limit, which is equal to 1. So since the exponential function is by itself an entire function, which means analytic everywhere, then our integrand will be entire. So we are able to deform the integration path. The original integration path runs along the real axis from minus a to plus a, but we deform the path into the blue path shown here, which goes on the real axis from minus a to minus 1, then goes down in an anti-clockwise direction around the unit circle, reaching the point plus 1 on the positive real axis, and then finally remains on the positive real axis up to the point plus a. Okay. Of course, a is a large number because we are interested in the limit when a goes to infinity. So in the drawing, we have assumed that it is larger than 1, definitely. Okay, once we have done this, we have represented our integral from minus a to plus a, let us call it I sub a, as an integral around an arc in the complex plane. Let us call the arc gamma sub a. Okay. Now we can represent our sine function in terms of complex exponentials. And in doing that, it turns out that for each of those complex exponentials, e to jz and e to minus jz, there corresponds a different integral. You can imagine introducing this representation of the sine function inside the integral and then splitting the integral into the sum, the algebraic sum of two integrals, one with the exponential with the positive exponent and the other with the exponential with the negative exponent. Now, for each of those new integrands, the point, the origin of the complex plane now becomes the pole, because we don't have any removable singularity anymore, but rather a pole of first order. Now, if we define the function phi sub a, as you can see at the bottom, like this integral of the exponential a to js z over z around the half circle gamma a divided by 2 pi j, okay, this function will depend on its argument s, and it's easy to see that our integral I sub a is the sum of the function phi sub a calculated once with the argument t plus 1 and another time with the argument t minus 1. Okay, we will write things in this way because now we are going to use Cauchy theorem in order to get an explicit representation of the function defined here at the bottom. In particular, it's easy to see that we can complete the path gamma A, which is the blue one, in two ways, using either gamma minus, which is the red path in the lower half plane, or the path gamma plus, which is the green path in the upper half plane. In particular, if S is negative, we will use the path, the red path here, because in this case, it is simple to see that the result is equal to 0. Why that? Well, because basically, if you consider the closed path constituted by the blue and red parts, well, inside this closed path, your function is analytic, okay? So having no singularities, we can apply Cauchy theorem, and the result is equal to 0. On the other hand, if you close with the green curve in the upper half plane, this is not true anymore, because in this case, your closed path constituted by now by the blue and green curves will wind around a singularity, which is the singularity at the origin, which is a simple pole with residue 1. So therefore, if you close downwards, basically we can write that our function, our 1 over pi times phi, is equal to the integral around the red curve. Otherwise, if you close upwards, you have that our function is equal to 1, the residue, minus the integral around the green part, which is what is written on the bottom right part of this slide. Okay, having seen this, we are now in a position to let the radius of those red and green circles go to infinity, which is what happens when you let the number a go to infinity, which is what we are interested in, because we wish to calculate the limit when a goes to infinity of this integral. So the radii of those circles, the red one and the green one, will go to infinity. What happens to the value of the integrals made around those half circles? Well, it turns out that this value may be maybe go to 0, provided S has the right sign. In particular, if S is a negative quantity, then the integral over gamma minus goes to 0 when the radius goes to infinity. Whereas if S is positive, then it's the integral around gamma plus to go to infinity, to 0 when the radius goes to infinity. Let us see that, for example, for the upper half circle, the green one, gamma plus, for which we can write that the absolute value of the integral that goes from 0 to pi, which is the limit values for the integration variable theta, which is the angle of the exponential evaluated on the half circle, and the half circle is in turn JSA, the radius, times e to j theta, okay? Okay, the absolute value of this integral is, of course, not larger than the integral of the absolute value. And the absolute value of the integrand is in turn equal to the exponential, the real exponential, e to minus sa sine theta. Now, by symmetry, this integration, which goes from 0 to pi, can be split into two equal integrals. And so we can write that this is equal to twice the value of the integral that goes from 0 to pi over 2. Why we do that? Well, because in the integration domain that's reduced, so from 0 to pi over 2, we have that the sine function, which is represented here in this small drawing, is a convex function, which means that it remains always above the secant, that is the straight line that joins the two endpoints. Okay, so basically the sine function is always larger than or equal to the value of the secant function, which is a linear function of theta with coefficient 2 over pi. Okay, with this inequality, which is technically known as Jordan's inequality, we are able to estimate this integral because we can now replace the sine function with the secant, okay, thus obtaining something that is larger because we have a minus sign in the exponent. So if we replace the sign with something that is smaller, then the value of the exponential will be larger. And now, what's the use of doing that? The use is that now we are able to calculate analytically the value of the exponential. So we are able to find the value of the blue integral, which is pi over SA times 1 minus the exponential of minus SA. And now it's easy to let a go to infinity and to discover that this goes to 0. So we have proved that the value of the integral around the upper half circle, the green one, goes to 0 when s is a positive number. With a similar reasoning, you will discover that the same happens for the red half circle when s is a negative number. Once we have this, it's easy to see that our function phi of s is equal to pi when s is positive and is equal to 0 when s is negative. And since our original integral ia sub a was written in terms of the function phi, then it's easy to derive the final result, which is the value of the Fourier transform of the sinc function, which is the limit as a tends to infinity of I sub a, and this is equal to pi when t is between -1 and +1, and is equal to 0 when the absolute value of t is larger than 1. So compactly, this is equal to pi times the rectangular function, which is equal to 1 inside -1 and +1, and is equal to 0 otherwise. Okay, so the residue theorem has allowed us to prove rigorously one standard result in the theory of Fourier transforms of functions on the real axis. Okay.
I mean, the rectangular behavior depends on the fact that you choose. I mean, when phi a is equal to pi, you choose the upper
yes.
boundary gamma plus, and so you compute the residue.
Exactly.
Okay.
Exactly. Otherwise, you go the other way and you have no residues and it goes to 0. Exactly. Okay. In short terms, it's exactly for this reason. Exactly. Another example to finish, another kind of real integral, which can be calculated by means of the residue theorem, the so-called Fresnel integrals, which occur in diffraction theory. For example, in diffraction from a half plane of an electromagnetic or acoustic wave by an opaque half plane, we have two of those Fresnel integrals. One contains the cosine of t squared inside the integral, which goes from 0 to a, and again we are interested in the limit when a goes to infinity. The other one contains the sine of t squared. Well, we of course do not know analytically the primitive of the integrands, so we are not able to explicitly calculate those integrals, but we are, as we will see in a moment, able to calculate the limit when a goes to infinity. When the upper integration limit is not equal to infinity, but is equal to a general number x, we speak about Fresnel integrals, the Fresnel functions c of x and s of x. Okay, in this case, we will make use of the nice contour represented here, which is sort of slice of a pie. So we have gamma 1 on the real axis from 0 to the radius r. Then we have an arc, a circular arc of angle pi over 4, which goes all the way to the bisectrix of the first quadrant. And then we go again to the origin running along the bisectrix, along gamma 3. Okay, we will make use of this contour and we will integrate the function e to minus z squared, which is an entire function in the complex plane. So therefore, Cauchy theorem tells us that the value of the integral of this function around the cycle constituted by gamma 1, gamma 2, and gamma 3 must be equal to 0. Now let us evaluate separately the contributions of the three parts of this cycle. Let us start again with the circular part, gamma 2, for which we will make a reasoning similar to the one seen before. So we will evaluate the absolute value of the integral around along gamma 2 as not larger than the integral of the absolute value of e minus z squared, which is in turn equal to r, the radius of the circle, t is the parameter, the angular parameter that describes the circle, and then inside as an integrand we have the real function e2 minus r squared cosine of 2t. Now again, the cosine function is convex inside the integration, inside the domain from 0 to pi over 2. So in particular, it is convex inside the integration domain that goes from 0 to pi over 4 in this case. So we can replace the cosine of 2t inside our integral by the second, which is always lower than the cosine function, which is again Jordan's inequality. And hence, we are able to evaluate, as we saw before, analytically the real integral here. And again, we draw the conclusion that when r goes to infinity, the absolute value of the integral around gamma 2 must go to 0, which means that in the limit when the radius r goes to infinity, the contribution of the arc at infinity goes to 0. So we are left with the contribution of gamma 1 on the real axis and the contribution of gamma 3 on bisectrix that we will now examine. As I said, by Cauchy theorem, now the sum of those two contributions along gamma 1 and gamma 3 must be equal to 0. Now, the contribution along gamma 1 can be calculated explicitly because we are on the real axis, so we integrate from 0 to r the function e2 minus t squared. When r goes to infinity, we obtain the standard Gaussian integral, which we know is equal to the square root of pi divided by 2. Whereas on the bisectrix, the calculation requires that we replace z with its value on the bisectrix, which is equal to t times e to j pi over 4. Okay, and if you perform the calculation, which is very simple, you end up with an integral of the function e2 minus jt squared, which, if you divide the real and imaginary parts, will give you the cosine and sine functions of t squared. And by definition, those are our Fresnel integrals, e sub c and e sub s, those we wish to calculate. Okay, the integrals along the real positive axis of cosine t squared or of sine t squared. So the integral around gamma 3 along gamma 3 is a linear combination of those e psi es functions. And so now we will put all pieces together. Cauchy theorem gives us that the sum of the integral around the positive real axis, gamma 1, which is equal to the square root of pi over 2, plus the integral around the bisectrix, which is this thing we have just calculated, well, this sum must be equal to 0. These can be split, separating the real and imaginary parts into a set of two equations, real equations in the two real unknowns, I sub c and I sub s, from which it is immediate to derive the values of those e sub c and e sub s, which turn out to be equal, and equal in particular to the square root of pi divided by 8. So in this way, we have calculated our limiting value of the Fresnel integrals with the cosine and sine functions. Those I have shown you are, of course, only two of the millions of examples that could be made of the use of the residue theorem for calculating integrals, not only complex integrals, but as I've shown you today, the residue theorem can be used to calculate also real integrals, and sometimes it is the only way to calculate real integrals for which we do not know analytically the antiderivative of the integrand. Okay, again, those are the references, the same of last time. For those who were not with us in the first lesson, the first book is a classical textbook by the Finnish mathematician Alfors, Complex Analysis. It's also very cheap if you buy it. Rudin is harder to read. It's a beautiful text which is divided into two parts, one devoted to real and the other to complex analysis. And finally, we have a more modern text with respect to alphors, which is the one by Conway, which is devoted to functions of one complex variable. Of this text, there is also a second volume, but the first volume is enough to cover what we have seen in this lesson and in the previous one. Okay, for today, that's all. If you have questions, you can, of course, ask. Also, you can write me for any other question you may have in the next days. Otherwise, we will see you next Tuesday, when I hope to be able to be also in presence in our department, but that will depend mainly on the health of my kids, which is a random variable. So I will let you know if I will be able to be there in person, or in any case, we will be able to give the lesson at a distance on Meet. Okay. So thank you very much for your attention.
Okay, thank you, and see you on Thursday.
Ok, see you all.
Thank you, bye bye.
Ciao Paolo, grazie.
Ciao, grazie a te.
Grazie, arrivederci.
Arrivederci.